Hello, in this video, I'm going to talk about neuron conduction velocity. So to start, what is conduction velocity? We are referring to the speed at which the impulse, or also called the action potential, travels along the length of the axon of a neuron. So there are several different variables that determine how fast that impulse is traveling along the neuron. So first is myelination. So myelinated axons conduct faster than unmyelinated axons. That's one of the main functions of myelination, is to speed the conduction velocity. Also, we need to consider the myelin spacing. So the amount of space or the distance between sections of myelin. So when there's greater distance between the nodes of Ranvier, so the gaps in between the myelin, so greater distance between them would result in a faster velocity. Also, the thicker the myelin sheath is, the faster the conduction velocity will be. So the larger the diameter of the axon, the thicker the myelin is, generally speaking. The next consideration is the temperature. So axons that are warmer conduct faster than axons that are colder. So when the ions that are traveling, that are the impulse essentially, when they become warm, they travel at a faster rate. So when we warm up for exercise or for physical competition, not only are we warming up our muscles and so getting our musculoskeletal system ready to move, but we're also warming up the nerves and the neurons that are carrying the action potentials to the muscles. So when we increase our body temperature by a degree or two by warming up, we're actually causing faster nerve transmission as a result. And then finally, the axon diameter. So larger diameter axons conduct faster than smaller diameter axons. So there are a couple of reasons for this. So first, large diameter axons are all myelinated. So there are no large diameter axons that are unmyelinated. So all large ones are myelinated, and the larger the axon, the thicker the myelin, which, as we've discussed, also is going to speed conduction velocity. So in contrast, small diameter axons, the very teeniest ones are all unmyelinated. So it's like the smaller the axon, the less they structurally are able to support myelination. So the very teeniest of axons are all unmyelinated. Then the slightly larger, so we're still talking about very small axon diameters, but large enough to support myelination, then in that case, those axons, because they are smaller, they will have thinner myelin than the larger diameter axons. But aside from myelination, the size of the diameter of the axon also makes a big difference in how much resistance there is to the flow of the ions along the length of the axon. So with a larger diameter for the axon, it means that there's more space inside of the axon where the ions can flow freely without making contact with the walls of the axon. So if we look at our picture here, on the top, we have a smaller diameter, and on the bottom, we have a larger diameter. So you can imagine, think about like if we have water flowing through a pipe. The water flowing through a pipe is going to flow faster through a larger diameter because there's less contact between the water in the pipe and the pipe itself. The more contact there is, the more friction there is between the water, or in this case, the ions, and the pipe, or in this case, the axon. So when we have a smaller diameter, that means that the ions that are flowing through are making more contact with the walls of the axon, which causes more friction, which resists the flow of axons. So in larger diameter axons, there's less of that resistance, which causes a considerably greater conduction velocity. In smaller diameter axons, there's a lot more resistance because there's more friction and more interaction between the ions and the axon. And so that causes a considerably slower conduction velocity. All right, thank you so much for watching this video, and I'll see you in the next one.